Section 2.5 is about the fundamental theorem of algebra. And so far, when we've been finding zeros, we've stuck to finding the real zeros of a polynomial, which would be the same thing as those x-intercepts. And anytime we would get a negative square root or a non-real solution, we would say like those aren't x-intercepts, and we would just not worry about those. And we always knew that if I had an nth degree polynomial that we could have at most n real zeros. So a fifth degree function could have up to 5 real zeros, but it could have fewer than that. But now if we expand our domain or our thinking to the complex number system, then an nth degree function will have exactly n zeros, and some of those could be complex zeros. And that's what the fundamental theorem of algebra says. It says if f of x is a polynomial of degree n, where n is greater than 0, then it has at least one zero in the complex number system. And the reason that's true is that every real number is a complex number where the imaginary part is 0. So if we had like the number 3, we could also write that as 3 plus 0i, making that a complex number. So this is where that comes into place with the fundamental theorem of algebra, where if I have a polynomial function, it has at least one zero in the complex number system, because this is considered a complex number, which we would write it as just 3. So like I was saying, all real numbers are complex numbers, but not all complex numbers are real numbers, because we could have that imaginary part. So the linear factorization theorem says that if I have a polynomial with a degree n, then I have exactly n linear factors where those factors are all complex numbers. And again, remember, complex numbers can also be real numbers. And we have, like I said, n factors if it's an nth degree polynomial. So let's look at the quadratic function x squared plus 4. So we know there are no real zeros with x squared plus 4, because if we do x squared plus 4 equals 0, subtract 4 at each side, we get x squared equals negative 4. Okay, we square root both sides, x equals plus or minus the square root of negative 4, which is going to say x equals plus or minus 2i. So I have two solutions, x equals negative 2i, x equals positive 2i. And this is a second degree function. We have two zeros, and we could write that as linear factors, as x plus 2i times x minus 2i. You know, remember the opposite of what we see, x plus 2i would go with this 0, and x minus 2i would go with that 0. So that we have that second degree function, and we have two linear factors, and both of them are in the complex, are a complex number with an imaginary part. So we have this one down here, g of x equals x squared plus 8x plus 16. And if we were to factor that, we would say, all right, what two numbers multiply to 16 but add to 8? That's positive 4 and positive 4. But we know we would use to write that as x plus 4 squared, because it's the same factor. Well, this is a second degree function, and we do have two linear factors. They are just happen to be the same factor in this example, and we would normally write it like this to simplify, but we could write it, it is possible to write it as a sum of two linear factors, even though there's just one zero at x equals negative 4. So if we look at example 1 down here, it says find all the real zeros of the function. So we have x squared times x plus 3 times x squared minus 1. I'm going to factor, so 0 equals, I'm going to factor that x squared minus 1 to x plus 1 times x minus 1. And we don't have all linear factors right now. We have x squared, which can be written as x times x plus 3 times x minus 1 times x plus 1. So let's just do that. So we have 5 linear factors, and each one of them we have x equals 0. Set each x equals 0 again. Then x equals negative 3. X equals positive 1. And then x equals negative 1. So this was a 5th degree function. We have 5 zeros. Even though these two are repeated, there are still 5 zeros. Looking at letter B, we have f of m equals m minus 4 squared, so we can rewrite this as m minus 4 times m minus 4 times m minus 2 plus 4i and m minus 2 minus 4i. So these last two look a little bit confusing because they have an imaginary part to them. And the only difference is the plus here and minus there. Well, remember, if we were to combine them, it'd be 2 plus or minus 4i, and they were just separated in this problem into two distinct linear factors. It is kind of like what we did up here when we split x equals plus or minus 2i into two separate solutions and then wrote those as two separate factors. So we really get these last two factors from this right here. So what that tells us is that for our zeros, we're going to have m equals 2 plus 4i, m equals 2 minus 4i, and then we have m equals 4 and m equals 4. So we have 4 zeros. 2 of them are repeated, these two, but we were able to write it as 4 linear factors, and each of them had a 0. Let's go to the next page. It says find all the zeros of the function and write the polynomial as a product of linear factors. So lucky for us, we can factor this one by grouping. So set it equal to 0, factor out a x squared, and then we're left with 3x minus 2. And then from here, we can factor out a positive 25, and we're left with 3x minus 2. So then we have x squared, 0 equals x squared plus 25 times 3x minus 2. Okay, well, we'll set each of these equal to 0. 3x minus 2 equals 0 is going to be x equals 2 over 3, and then x squared plus 25 equals 0. X squared equals negative 25, and when we square root both sides, x equals plus or minus 5i. So our solutions are this is a 3rd degree function, so we should have 3 solutions. We have x equals 2/3, we have x equals 5i, and x equals negative 5i. And if we were to write this as a product of linear factors, we have f of x equals, well, this is a linear factor already, 3x minus 2, so we can write that. The x squared plus 5 is not a linear factor because it has an x squared in it. So then we have to look at our zeros and say, okay, well, if this was x minus 5i, when I substitute positive 5i into it, I get 0. And then same thing here, I can do x plus 5i, because when I substitute negative 5i for x, I get 0. So this would be our linear factorization. All right, in example 3, it says find all the zeros of the function, write the polynomial as a product of linear factors, and then use our factorization to determine the x-intercepts of the graph of the function, and if need be, for it, use a graphing calculator to verify that those are, or that the real zeros are the only x-intercepts. So we have f of x equals x to the fourth minus x squared minus 20. This is in quadratic form, so we can factor this and set it equal to 0 as x squared minus 5, x squared plus 4. So now we have two quadratic factors, and we want to find our zeros and make them a product of linear factors. So we're going to set both of these equal to 0, x squared minus 5 equals 0, and solve that. X squared equals 5, x equals plus or minus the square root of 5. Then here, x squared plus 4 equals 0, x squared equals negative 4, x equals plus or minus 2i. So our zeros, we have x equals negative square root of 5, x equals square root of 5, x equals negative 2i, and then x equals positive 2i. So our factorization, be f of x equals x plus the square root of 5, x minus the square root of 5, x plus 2i, and x minus 2i. Right, I have four linear factors, and this is a fourth degree function, and I had 4 zeros. Now, it doesn't have to be 4 different zeros or 4 different linear factors, but we should have 4 of them. Letter B, we have g of x equals x to the fourth minus 16. Well, we can factor that. That is a difference of squares. So this is going to be x squared minus 4 times x squared plus 4. Well, we can still factor this. That is another difference of 2 squares. So really we're going to set equal to 0. We have x minus 2 times x plus 2 times x squared plus 4. And then we're going to set them all equal to 0. X equals 2, x equals negative 2, and we just solved this in the other problem. Okay, and it's still right here. We got negative 2i and positive 2i. So then our linear factorization is going to be x minus 2 times x plus 2 times x minus 2i, or x plus 2i, x minus 2i. And that would be the linear factorization for this one. It is a fourth degree function, and we have 1, 2, 3, 4 zeros, or sorry, 4 factors, and we also had 4 zeros. Now look at the imaginary solutions we have. In both of these problems we had minus 2i and plus 2i. Up here we had positive 5i and negative 5i. Here we had 2 plus 4i, 2 minus 4i. So what that shows us is that complex zeros always come in conjugate pairs. So if we have a zero that is in the form a plus bi, then a minus bi is also a zero automatically, even if it's not listed. So if 5 minus 6i is a zero, then 5 plus 6i must also be a zero. That's what it tells us. That's what the conjugate pairs tells us, that they have to be come in conjugate pairs. And it's because when you take the square root, you have a plus and a minus when you take the square root. So example 4 says find a polynomial function with integer coefficients that has 0, 2, and 3 plus I as zeros. So f of x equals, we have x for the 0, we have x minus 2 for 2, but for the 3 plus I, we're going to do some scratch work over here and say, well, if 3 plus I is a 0, then 3 minus I must be a 0 as well. And now we're going to think backwards like we did with the rationals, the radical zeros. And say, okay, how did we get 3 plus I and 3 minus I as zeros? Well, it started with x equals 3 plus or minus I, because we had 3 plus I and 3 minus I. Okay, well, now let's get everything to the left side and make this equal to 0. Subtract 3 from both sides. X minus 3 is equal to plus or minus I. Then we square both sides. We have x minus 3 squared, which is x squared minus 6x plus 9 equals, well, I squared is negative 1. Okay, well, if I squared is negative 1, we can now add 1 to both sides, so we get x squared minus 6x plus 10 equals 0. So this is the quadratic factor that got us these zeros, 3 plus I and 3 minus I. Now, the problem here did not tell us that we had to have linear factors, so we can be good with what we have right here. Now we have to multiply all this out. I'm going to multiply this first. So we have f of x equals x squared minus 2x times x squared minus 6x plus 10. And then we'll double distribute everything. X squared times x squared is x to the 4th. X squared times negative 6x is negative 6x to the 3rd. And x squared times 10 is positive 10x. And then negative 2 times x squared is negative 2x to the 3rd. Negative 2 times negative 6x is positive 12x squared. And then negative 2x times 10 is negative 20x. So then we can combine our like terms. F of x is equal to x to the 4th minus 8x to the 3rd plus 22x squared minus 20x. And this would be our polynomial in general form that has the zeros has solutions of 0, 2, 3 plus I, and 3 minus I. So I know that this can be confusing because now we're like going a step further. We're talking about the complex numbers, imaginary numbers, and all that. But if we apply what we had before and push forward with it, it doesn't become that much of a stretch. Right, so thanks for watching the video. Make sure to like it and subscribe.